Alrighty, good morning, guys. Can you hear me?
Yes, we can hear you.
So before we get started on the material for today, I want to see if there are any questions. I know that you have a homework due tomorrow, so just want to see if I can help out with some of the homework questions, if you have any. Yeah, I mean, if you, this is there's also office hours tomorrow, but if there are questions about the homework, then I mean, ask away. Yeah, so if the questions are related to C++ code, then you need to use the TA who has office hours tonight and tomorrow night. I mean, I'm happy to help you with all the other questions. Yeah, so the the TA's office hours are they're there to help you guys with your C++ code. It has been many years since I've looked at C++ code. Are there any questions related to the homework about non-C++ related issues? Okay, then please use the TS office hours, and I will also be here tomorrow morning in case something comes up. So what I had in mind for today is we're going to continue with the so what we're doing is we're looking at numerical methods for ODEs, and what we're going to be doing first is we're going to consider this method that's called the trapezoid. And when we do PDEs, this is what's going to become Crank-Nicholson. And this is what will be needed for homework 5. So we're going to spend some time talking about this way of solving ODEs numerically. Then there's a trick called Richardson extrapolation. We also gonna need that in homework 5. This is a way to speed up. Your numerics. So we talked about, this is a lot about speed. Now we're going to move into accuracy. So we're going to talk about stability. So this is how small time steps, you need So I'm guessing this here is going to take most of today's lecture, but I am hoping that in the end here we can start looking at PDEs. And so primarily here what we'll be looking at is the heat equation. Okay, so let's start with introducing this trapezoid method. So we have an ODE. We have an ODE of the form f prime of t. This is this f of t. And let me just drop the t over here. So we could also consider f and then a t over there. But let's just let's keep it a little bit simpler and drop the t over here. It doesn't matter much for what we will be doing. And then there's an initial point, say A. And here this could be multidimensional. It could be multidimensional. But in your homework 4, in the Stein model, you have you have 3 coupled ODEs, right? So it's true that the system that you're having, it's a triagonal system, so you could solve one at a time, but you could also solve all 3 of them at the same time numerically. Okay, so you have an ODE of this sort. Could be high dimensional, could be multidimensional, and we looked at different schemes. And we call those ones that we looked at. We looked at the explicit Euler. So here you would have Fn plus 1. This would be Fn plus h, and then f, that function up here, evaluated at Fn. And then the initial point, this was A, right? So, so what we have in mind here is that Fn approximates f of Tn, and Tn is equal to n times h for a small time step right. So the points, this is going to give us a sequence of this recursive formula here. This will give us this produces f0, f1 up to fn recursively, right? And we are hoping that fn approximates this value. So here, f of Tn, this is this actual solution to the ODE on here. Right, so the n, when you see Fn, this is the approximation. This is a single point. This one over here is a function evaluated at Tn. Like we saw, for example, last time that when the initial points are the same, so when Fn equals f of Tn, well then the difference of Fn plus 1 minus f at the actual correct value, this here is O of h squared. So this was the explicit Euler. We also have the implicit. So it's very similar. All it does is that instead of having Fn here, you'll have Fn plus 1 is over on the right hand side. So your Fn plus 1, you get that by solving an equation like this one. So here you have to solve. This is implicit because you need to solve for Fn plus 1. Right, so if f here is complicated, this can present a challenge. How do you solve an equation like this one? If capital F here is like a square, then you're going to end up with two solutions. But nevertheless, this is the implicit Euler method. And again, this was also the difference here. We saw that last time. If the two previous time points coincide, like we start out at the same one, right? So F1, how does that compare to the other one? Well, we're making an error here of big O of h squared. So the one I want to do more carefully today is the trapezoid method. So the trapezoid. So the trapezoid method, this is what will be important for us when we do Black-Scholes PDE. The trapezoid method says you take a mixture of the implicit and the explicit. More specifically, you take half of this one and half of this one, and then you add them together. So the trapezoid says you take Fn, this should be, right, this here should be, and you have to solve here. You take Fn plus 1, this should be Fn plus, and then you get a half here, and then take the mixture of these two. So this is again implicit because you have Fn on both sides, and you start out at whatever initial point, we call it A. So this here is again, you need to solve. You again need to solve for Fn plus 1. This is an implicit method. So there's work to be done here. And you can see when you looked at the explicit and the implicit Euler, got the same error estimate. This O of h squared, what we derived last time. Both of them have the same power over here. So when you look at it, it seems like you should always use the explicit because here you don't have to solve. This one here requires more work and you don't speed up. But we should see a little bit later that there might be other reasons why you want to choose the implicit one, and it's down here in this stability. There might be reasons related to stability for why you would want to use the implicit instead of the explicit. But we'll get to that in about an hour or so. Right now, we're looking at the trapezoid method, and it's a mixture of the two, and it's an implicit method because fn plus 1 is here, and fn plus 1 is over here as well. So here you would have to go from fn, to go from the nth point to the nth plus 1th point, you have to solve an equation to get that. This is something to keep in mind because this can be, that can be non-trivial. So we want to figure out what's the order. What is the order? Right. So what you do is you make the assumption that you start out, you're precise at the previous point. So you have if n is exactly equal to the correct value, and then you want to look at what's the difference between fn plus 1 and then the actual correct value. What does that belong to? Some order here. And what's k? And before we had 2 and 2, and now we're going to get a different value for k. And let's try to figure out what it is. Any questions up to this point? Before I start doing the calculations, are there any questions? Okay, so we're gonna what are we gonna do? We're gonna expand. That's what we did last time. It worked. So let's try that again. So we're gonna expand. We're gonna expand f of t into a Taylor. So we're gonna write here if at that point tn plus 1, right? So this is the correct solution. We're going to write this here as the value it had at the previous one. And then we want to do a first order would be f prime and then say at tn. A second order would be 1/2 h squared if double prime of tn. And then the error term O of h to the power 3. So that was the first order of business. And so that's the term I have here. And then this one here, the fn plus 1, this is the one I will get from the formula in the trapezoid method. So what will I do? I'll take f tn plus 1 minus fn plus 1. I'll write out what it is. I get all the stuff here. F tn plus h prime tn plus 1/2 h squared double prime tn plus the error big O of h to the power 3. That was Taylor. Subtract away minus, and then the formula that's provided by the method. So this was fn plus, and what was the formula? It was up here, 1/2 h, and then fn plus fn plus 1. How big is this error term? Well, we can see some things, right? We're doing local analysis, so f of tn is exactly the same thing as f of n. So I can see that these two here, they're equal. Right? That was the local analysis hypothesis. We make the assumption that we are the same, we're precise when we start, and then we want to see the error we make over the next time step. So that was the first one. Now, what else do we have? Well, because this is true, I will also know that this part here, because fn is exactly f evaluated at Tn, I would have that this is f at f of Tn. Okay, but then if that's true, if that's true, then I can use the formula that this is exactly f prime, right? This is exactly f prime at Tn. So I'll be able to plug that in. F prime at Tn, and I do that because you see there's a term like that one up here. So I can now simplify a little bit. Simplify a little bit. These two terms canceled. These two terms canceled, and here I had minus a half of this f prime that I have up here. So I get a +1 and minus a half. It leaves me with a half of h f prime at Tn. And then I have the higher order terms, 1/2 h squared f double prime of Tn plus O of h to the power 3. And what else is left downstairs? This guy I already took care of. This term here, he merged with this one. I got the half, and then there's this one here that's left. So I get minus 1/2 h times this guy. Okay. So I need to get rid of, there are lots of terms here, and somehow again, I would like to have stuff to cancel out. And so what I propose to do is to add 0 here. So this is h over 2. Okay, so that's a coefficient. And then I'm inside here, I'm going to take f evaluated at the correct point, f of Tn plus 1. So just as before, when I plug in f evaluated at that point, I'm going to get the correct one. So if I subtract away here f prime at Tn plus 1, this is going to be a 0. Right? This term here is 0. So I did nothing else than add 0, and that's of course not going to disturb the equality sign. So I got down to here. And so what do I do next? So the next thing that I do is these two terms here. You see, one is evaluated at the one is evaluated fn plus 1, and the other one is evaluated at the correct solution f at evaluated at Tn plus 1. So here there is a Lipschitz property that we all used last time to make this difference small. And then I have this one here. And how would I attack this one? Well, I have that term up here. I need to link these two terms with each other. So the proposal is at this point is to expand f prime in a Taylor. So how many terms should we have this time around? I think we only need 2. So let's write this here as, that's the term I want to expand. So I want to have f prime Tn plus 1. I can get that out by evaluating it at f prime of Tn. And then that was the initial point. Do the time step. Then I need f double prime Tn. And then an error term h squared. And then that's going to link this last part with the first part. And then I have to deal with this difference here. And this is where I'm going to use the Lipschitz, sorry. So also remember the Lipschitz property. It says that if I take f evaluated at a point, say f minus f evaluated at another point, say g, take the absolute value, you're going to get something that is less than a constant, c lib, times the difference between f and g. So we're doing this analysis here under the assumption that that function that controls the derivative, that it has a Lipschitz property. Okay, so now what I want to do, so that Lipschitz property is going to take care of these two terms. The expansion is going to link this term with the first term. So let's see it in action now. And let's see what we get when we combine everything. So I'll take absolute value f at tn plus 1 minus f at n plus 1. That was this one. Take absolute value of these things here. What will I get? What will I get? I will get the Lipschitz. The Lipschitz feature would come out here. That would be 1/2 h. And then you would have the Lipschitz property, the Lipschitz constant. And then the difference, this would be f tn plus 1 minus fn plus 1. So that was these two terms. Let me move on to the other ones. And here I would have, what would I have here? I have minus f prime at tn plus 1 times h over 2. So you see that term is going to be exactly the first one. And then the next term will be h, so that'll be h squared divided by 2 with a minus sign. And here I have plus 1/2 h squared if double prime, so d will cancel out. Then I have O of h3, and here I have h divided by 2 times O of h squared. It's again going to be O of h3. And so then we combine. The half, is that the one? That was the right one. So then we combine, we're going to get that f of tn plus 1 minus fn plus 1. I move it to the other side and I divide over. This is going to be bounded by 1 over 1 minus 1/2 h, and then the Lipschitz coefficient times O of h3, which is of course O of h3. Right, so trapezoid. So the trapezoid method has order 2. And that's different. So this is higher than Euler's methods. So there's an advantage here to use the trapezoid method. It gives us a faster rate of convergence. It gives us this h to a higher power than the other two. Is there any questions on this part? Any questions on what? So we have 3 methods now. We've studied in a fair amount of detail. So the trapezoid was the new one today compared to the other ones. And we have 2 first order methods, and then we have 1 second order method. The next thing I want to discuss is this Richardson extrapolation. Find my notes. This morning. So what we had now is we're moving down here. We did the trapezoid method. We're going to return to that down here in the PDE with the heat equation and Black-Scholes. We're going to talk a little bit about what's called Richardson extrapolation. And this is something that will help you achieve a higher order of convergence when you do your numerics. And it's kind of it's like free. It's not very involved in terms of computations. It's just a trick. So let me try to outline how that works. So when you do Richardson, so Richardson, so there are links here. There are links on, so I should say that there are links on the syllabus to notes where you can find more detail, both regarding these methods that we talked about here, but also about Richardson. There'll be 3 links. There will be 3 links today to 3 different teaching notes where you can find more detail. Okay, so Richardson extrapolation. There are two sides to it. There are two applications. So one, it is to speed up your method, speed up numerics to a higher order convergence. And the other one is you can actually test your numerics convergence order. So you're doing your numerics and you have a time step of h, and you do your numerics for different time steps, and you're interested in estimating, is it really the power 3 that we're seeing up here when you do an example, or is it something else, right? And so let me try to walk you through how to do this. How can you achieve these two things? And it's not that bad. The keyword, if you want to Google, is called Richardson extrapolation. So say you want to compute, A by taking limits of an approximation A of h for h positive. Say you want to do this. So A is some quantity you want to compute, and you want to take limits of an approximation where you have this discrete parameter h positive in there. Say that these two are linked by an error, A minus A of h. That difference, it's O of h to the power k. This is the kth order, right? So we could just say, write it like this. that difference is in there, or equivalently, you could say that that difference is bounded by some constant c times h to the power k. Where c is a constant. Where c is a constant. Right, so this is the case in some of these numerical schemes that we looked at. We have had 3 different schemes, and you've had at least 2 different Ks in there. So what we want to do now is we want to improve the way of approximating A. So we want to use something else instead of A of H. We want to correct A of H just a little bit and obtain a better order of convergence. And the way to get around that is that, again, you expand. We always expand when you do this sort of analysis. It's always Taylor expansions that you use. You expand. You expand A of H in Taylor expansions. So you're going to do two different H's. So let's do H1. H1 is bigger than H2. We will always have this relationship that H1 over H2, say, is 2. So what will we do? So if we expand this, then we will have A of H, say 1. This would be the correct point. And then there'll be a coefficient AK, and then it'll be H1 to the power K. Right, that was because we had a K up here. And then there'll be some higher order terms. There'll be like an AM H1 to the power M plus yet something else, O of H1 to the power M plus 1. Right, so this is by the assumption that we have a K up here. This is the reason we're going to get a K here. Right, and then the next order is going to be M. M is going to be bigger than K. Typically, M here is going to be K plus 1, but it could be that it's even higher. So I'll just put an M here. And then I'll do the same thing for H2. So it'll be the correct point. And then I'll have AK H2 to the power K plus AM H2 to the power M plus some error term. Right, so I'm computing my approximation here for different H's. And so what I want to do is see if I can make a correction here. So instead of using A of H, I want to use a correction to this thing and obtain a higher order. Okay. So, and it's going to be not the only complication is going to be to keep track of all these indices here and not mess them up when we do it. So let me try to take it step by step. So you multiply the quantity H1 over H2 to the power K on this last line. So when I do that, I'll get and subtract from the first line. Subtract from the first line. So that will be A of H1. So I'll have A of H1 minus And then this is a ratio times A of H2. What does that come to be? See if I can get it to work. So we will have, we'll do it in 2 steps, maybe. Okay, so we have the first one. This is A plus AK H1 to the power K plus AM H1 to the power M plus, then is O H1 to the M plus 1. That was the first one, and then I subtract away. And subtract away, I have the multiplier H1 over H2 to the power K, and then everything inside here is going to get, I have to plug in what A of H2 is, A plus AK H2 to the power K plus AM H2 to the power M, O of H2 to the M plus 1. So I'm going to do a couple of things now. So here we're going to be using, so for the next equality sign, I'm going to be using this, that H1 over H2 is equal to 2. So here I'll use that H1 over H2 is equal to 2. Okay, so then that's a 2. So I'll have here A times, and then I'll have 1 minus 2 to the K. So that was this first term, and then it was that term. And then what else will I have? I'll have AK I have AK I'll have AK H1 to the power K minus, and then what we have down here is H1 to the power K. I put AK outside, so here I'll have minus H1 divided by H2 to the power K times H2 to the power K. That's where the miracle happens. So this term here and this term combine into what I have here, and this is my 0. And then we move on, we have AM, and then I'll have H1 to the power M. I'll have that ratio minus H1 over H2 to the power K, H2 to the power M. Plus, and then the error terms, the higher order error terms, plus, what will they be? It'll be the first one, O of H1 M plus 1 minus, and so this is again a 2 to the K, O of H2 M plus 1. So you can see now what happens here with this K is that it the K is dropped out. there's no h to any power k, like the higher order term now is going to be something with h1. So I can write this here more compactly as a times this thing. That one is gone. I can take advantage of h1 over h2 being 2, so I can pull out, say, am here, and I'll pull out h2. If I pull out h2, then I'll get the ratio. This will be 2 to the m minus, and then this one here was 2 to the k. This one here would be h1 is equal to 2 times h2, so everything here is just O of h2 m plus 1. So you can see it dropped. It went from having terms in here that would involve ak to the power k. Now I just have the next order term up. So I can solve for again, this ratio here, this is 2. I can solve for a here. Get a is equal to this difference here, a of h1 minus 2 to the k, a of h2. Minus am h2 to the m, 2m minus 2k, and then this guy, keep him outside here, O of h2 to the m plus 1, and then divide over by 1 minus 2 to the k. And so what we see here is that, so while a of h1 approximates a to the order k, we'll have that this difference does much better. We'll have that a of h1 minus 2k, a of h2 divided by 1 minus 2 to the k approximates a to the order m. So this is a better approximation than each. I mean, this is the same. A of h1, I should also say a of h2. Both of them do just to the order k, a of h1 and a of h2. You approximate a to the order k. If I mix them according to this formula, I get a higher order. So by computing the individual approximations, forming this new ratio, I get a better approximation. But of course, this involves this requires that you know k. So you should always test your numerics for k. You always, so you might know k theoretically. You might know k theoretically, like for the implicit and explicit method and for the trapezoidal method, you know K theoretically, but that's done under a bunch of assumptions, and these assumptions may or may not be true for the particular problem you're looking at. So you should always try to figure out what K is in your numerics. And so how do you do that? And that's the second part of the Richardson scheme. Right, so we found a way to speed up your numerics. And the second one here is you should also test your numerics and just backtrack and figure out, does it really have the right convergence order? So let me show you how to do that, also using Richardson. And the way to do it is, the way to do this is to pick three values. So I have H1 bigger than H2 bigger than H3, and we're going to have the relationship is going to be like before. H1 is the biggest one, so when I divide over, I want to get 2. So to test out the order, we need three of them. Then what you do is you say, I'm hunting what K should be. So I will look at, if I have a K order method, I know that A of H1 is going to be equal to A plus, well, it's going to be roughly equal to A plus a coefficient AK, and then H1 to the power K. I'll put approximation here instead of writing these error terms out here again. This is just a little bit easier for now. So this is roughly the same thing as AK H2 to the power K. Like K is the unknown we're trying to get our hands on, and then you have H3. This is A plus AK H to the power H3 to the power K. So you have these three. And then I'll subtract. This here is going to imply that A of H1 minus A of H2. The A's will cancel. There'll be a common factor of AK. And then I'll have H1 to the power K minus H2 to the power K. And of course, as before, I can pull out, say, H2. And then I'll have the ratio. This will be 2 to the K minus 1. And I'll do the same thing for H2 minus A of H3. It'll be the same formula. It'll be AK H2 minus H3 to the power K. I'll use again that the ratio between H2 and H3 is exactly 2. I'll pull out H3. And so here I would get 2 to the K minus 1. And so comes the miracle, because if I divide, I'll have A of H1 minus A of H2 divided by the bottom part. And so we look over here, a bunch of these things will cancel out. The AKs in particular, they cancel out. And I'll get here H2 to the power K divided by H3 to the power K. This will be exactly 2 to the K. So this ratio, if I have a K ordered method, this should be roughly equal to 2 to the power K. So there is a way to look at your numerics and figure out what the order is. And so that will give you that K. And so now if you know what K is, but then you can go back to your approximation. You can make this correction here, and then you get a higher order method. Any questions about this? This can seem very abstract, but let me just show you how it will look like in your in your homework, the next one. Let me show you how it will look like in the next homework. Homework 5. To run the code in a second. So this here is the this here's the next homework. This is written here for a Black-Scholes PDE. That's not really important, but somewhere down here, it asks you to estimate the order of convergence and then perform this, which is an extrapolation. So there's a parameter. We're going to be talking a lot more about these Black-Scholes PDEs and this stuff. This is what's going to come later. But if you flip down to the numerics that I'm asking you guys to do, is so we have we have 3 stock prices, and then we have this parameter. This here is my age, or 1 over age. You see, I double it up every time. I go from 100 to 200 to 400 to 800 to 600. This is to have that coefficient to be 2 that we saw before. And so I have the exact solution in Black-Scholes, but then I have the numerics coming out of my code based on this trapezoidal method, or Crank-Nicholson as what it's called. And so I've computed this for a bunch of different h's. H's is 1 over these numbers out here in the second column, and I can estimate the order. Right, so that was what we did here in the very end. You can estimate the order, and you can see this order here is very close to 2. Okay, so now if I know what the order is, I can extrapolate. And it's kind of remarkable to see what the extrapolation does compared to the original numbers. Right? These are the numbers that come out of the code. These are the correct numbers that are coming out of Black-Scholes formula. I can extrapolate like this number here and that number here, these two. If I can highlight them at the same time, I cannot highlight them at the same time. The second row, right, when I compare Crank-Nicholson's numbers, the numerics coming out of my code, compared to the Black-Scholes numbers, and then I look at what happens when I extrapolate. That correction over here on the right-hand side, it is somewhat better than what you have here. And it doesn't require any additional work. So it's kind of remarkable that this little trick, it really does work extremely well in something like a heat equation like this Black-Scholes that we're going to be talking about in a second. And it doesn't involve, as you can see from what we did, it's just straightforward manipulations. It's just ratios and differences, and you just have to put the coefficients in the right spots, and it works. And you get this 2. The order is really 2. And this order we're seeing here, this 2 we're seeing here, this is coming from Crank-Nicholson. That's coming from the very first calculation we did, where we looked at the trapezoidal method, and it had this O of h to the power 3. What we're seeing here is 3 minus 1. It's just that 2 that's coming out here. So let me pause here and ask if there are any questions. So on the syllabus, let me just show you while we're while we're at this looking at documents. So what I'm doing on the syllabus is the syllabus is getting updated on a weekly basis. So you flip here to the last part. You'll see the what we're going through in the various lectures. And we down here, it's April 1st today. So what we're talking about is Richardson extrapolation, and the next topic that's going to come is stability. So there are links here to notes where you can find more details. So there'll be a third one coming up. I only put two here. There's one more set of notes that I've been using for these lectures, and I'll put that in here too. You can also see here at the very last line the date for the reports, for the final reports. I talked to Anna a couple of days ago, and it's May 6th. That's early in the exam period, and this is made to spread out your burden over the exam period. So Anna created a schedule, and this was the dates that she gave me. This is not a date that I have picked. This is coming from Anna. So this is early in the exam period. I should also say that the next 2 Thursdays, the lectures are going to be a little bit shorter, and this is twofold. On one hand, I have meetings that I need to go to, and on the other hand, it's also to give you guys some more time to get started on these projects. So the load in the class is less here after spring break than it was before. There were 4 homeworks before spring break, and then 2 here after spring break. Homework number 4 got pushed a week, but the idea is that it should be a lighter load after spring break, because you have these final reports that you need to get working on. So please try to take advantage of this time that you have, so it doesn't get so crammed towards the end of the semester. Right, I'll put one more here, and then there'll be 3 sets of notes. There'll be one of them is Black Scholes. This is this last one here. The first one here. This is about this PDE that we're doing, and then I'll put a third one that has to do about these ODEs and Richardson extrapolation that we just did. I'll put it up on the website when today's class is over. Okay, are there any questions or comments about what we've done so far? So we talked about the trapezoid method, we talked about Richardson extrapolation, and now we're down here at stability. So this has to do with, are these methods stable? Like you have 2 horses, right? So you have as often is the case in life, there are 2 horses. There are 2 horses running in opposite directions, running away from each other, right? So on one hand, you want to have speed. And on the other hand, you want to have accuracy. So if you want to have accuracy, you have to slow down. And if you want to have speed, we have to let go of accuracy, right? So you have 2 horses running in opposite directions. You can't have both. And speed, this is this order of convergence, right? This is the order of convergence. And accuracy, this is like how small do you need? How small do you need H? Okay, so the way that we're going to do stability is we're going to look at our favorite ODE, which is we're going to look at a test problem. It's always something along this test problem that people look at when they talk about accuracy. So you're looking at a test problem, this is an eigenvalue problem. It's also really just the exponential. Right, so you take a coefficient lambda, which is complex. You take one of those, and then you just consider the ODE. F prime of t is equal to lambda f of t. And then you look at f of 0. This is equal to 8. Right, so f prime is equal to f. This is an exponential, and this is the initial point. It's just a. So if I look at, so then we use the explicit Euler. Start with him. Look at the explicit Euler. So I'll have f n plus 1 would be the previous one. I'll take my h. And I'll take my lambda. Lambda is my complex number. And then I'll take the derivative. This is my f of n. And so I could combine. I'll get here that this is 1 plus h lambda to the power times fn. I'm teaching back here.
I want to ask you a question.
Close the door, please. So this was f. This will take us from fn to fn plus 1, and so we could iterate this. We could now insert what fn is in terms of fn minus 1, and so we would go all the way down to a times 1 plus h lambda, and then we would have like n plus 1 here. So we could iterate this backwards, and we get something like this. So the criteria for accuracy is, or stability. So stability is, so we say the method is stable if this fn plus 1 goes to 0 as n goes to infinity. So when does that happen? So for the explicit Euler, that happens exactly when this coefficient we're raising to the power n plus 1 is not big. This here happens exactly when 1 plus h lambda is small, less than 1. So if you look at it in the complex plane, so this is the complex plane. So up here we will have plus I, and down here we will have minus I. And so we have h lambda is equal to 1, then I'll have a minus a 1 here, and then I'll have a circle. So when h lambda is inside here, we are small. So this is a bounded region of C. So in other words, you need your time step to be so small that this one here is less than 1. What about the implicit Euler? So we did the explicit, we'll perform exactly the same calculation, but we'll do it now for the implicit Euler, right? And so the only difference is where you put the n plus 1. On the right hand side, you'll have an n plus 1 here. So let me try to do that. If I do the implicit Euler, then I would have the same problem we're testing out. This one here. The implicit Euler would say that fn plus 1 should be fn plus lambda h fn plus 1. And so this is where we have to do more work. We have to solve, and we can do that. We can do that. This means that fn plus 1 times 1 minus lambda h. So we see there's a sign change now. You get this minus lambda h here. That this has to be fn. Okay, so this means that fn plus 1 has to be fn divided by 1 minus lambda h. And then we can iterate as before, go all the way back to f0. So this here will give me a, that was f0. That was what we started out with. And then we'll have to divide by 1 minus lambda h to the power n plus 1. So when is this stable? Well, we're not going to get something else. So we're going to get here that fn plus 1. We're going to get here that fn plus 1 converges to 0. This is dictated by this one here being big. So this is 1 minus lambda h being bigger than 1. So you see, it's quite opposite to what you had up here. If you draw that picture in the complex plane, so again, this here is the complex plane. We put a 1 here, we put a minus I down here, and put an I up here. Then you have a ball. This is true. Then you have everything outside the ball. So this here is an unbounded region. So this is where you can see the benefit of the implicit Euler over the explicit one. You do more work because you have to solve for fn plus 1. But what you're going to get is a much bigger region of stability. And so that's beneficial. This is the advantage. The difference between a bounded, like you have a ball, and here you have a complement of a ball, and the complement of a ball is this unbounded region. So you just need this property here. And the third and last method that we talked about is the trapezoid method. So let's test out his region of convergence, the trapezoid. That was the one we started out with today. So let me just recall what the trapezoid method says. It's fn plus 1 is equal to, and it's this thing where you also have to solve to get fn plus 1. This is fn plus, and then you have this mixture. You have the mixture of the implicit and explicit. So on the right hand side, you get 1/2, and then of each. So this is 1/2 lambda fn plus lambda fn plus 1. So again, you have to solve. So I'll move the part that has to do with fn plus 1 to the left hand side. I have fn plus 1 times 1, and then I get minus 1/2 h lambda. And this should be, then I'll have fn here times 1 plus 1/2 lambda. And then I can solve. I divide this thing to the other side. I get that this is fn times a ratio 1 plus 1/2 h lambda upstairs, and then downstairs 1 minus 1/2 h lambda downstairs. And then I can iterate it. I can plug in what is fn minus 1 and so on, and I'll end up with f0, which was a times, and then this ratio here, 1 plus 1/2 h lambda divided by 1 minus 1/2 h lambda, and then to the power, say n plus 1. And so when is this stable? So again, I need the absolute value here to be bounded by 1. So if I look at C just to be h lambda, so keep in mind lambda is a complex number, h is a small time step. Right, so this here is a complex number. So what I need is I need 1 plus I need 1 plus 1/2 z divided by, well, we should just take this to be 1/2 here. And then 1 minus z, I need this to be bounded by 1. All right, so I need 1 plus c to be less than 1 minus c. And so what I need here is that the real part of z should be negative. And so on a picture, this is complex plane. I'll have everything over here. And this is again, this is an unbounded region of C. So it'll tell you something about the it'll tell you something about like these implicit methods. They have unboundedness in terms of stability. So you have a lot more freedom in terms of choosing what h is. It works for many more h's. Whereas for the explicit Euler, the h that you choose has to be such that you end up in this ball here. It can't be that big. So that's what the implicit method buys you. You have more flexibility in terms of choosing the time step parameter. Okay, so this was a little bit about stability. So these methods here, they are stable. I mean, these sets here, they're not empty, but you have to be a little bit careful about when you use this explicit method. Like you have to think about how big your parameter h can be if you want to have stability. Right? Now, of course, you want to have your parameter h to be big to get speed, but then you might not have stability, and so then you need to low range. Are there questions on stability? We didn't spend so much time on stability. We spent a lot more time on the speed of convergence. Are there any questions on it? If not, then we're going to move into PDEs instead of ODEs. We started out doing the ODEs because we're going to use these approximations to study PDEs. So now we're down here in the PDE part. Let me just show you one node that we're going to be using. So one of the links up there will take you to a teaching note. I don't know if you can see this, maybe it's too small. Let's see if I can get this thing lower. So the last name is Monk, M-U-N-K. He's at Copenhagen Business School. He has a teaching note here. It's like 10 pages long. And it's about Black-Scholes PD. I have talked about, Hall's textbook a few times, and let me just bring that one up one more time for you guys to see. There's a large section in Hall's about exactly this. So if you flip into Hall's if you flip into Hall's book on numerical methods for flip into Hall's book on numerical procedures, there's a chapter over here. It's hard to see. It's this 19.8. So numerical methods. This is over in 435, and so we're looking at finite difference methods. This is what we're doing. We're going to get a PDE now, and so you can see, you can start recognizing the words now. There's something here called the implicit method. There's probably something somewhere called the explicit method. There's the explicit method over here, and then the it should be, no, he didn't do that. There's the Crank-Nicholson. That's the one that we all love. We're gonna love soon. That's the Crank-Nicholson. That's the Trapezoidal method. So if you have Hall's book, there is also a source in Hall's book where you can read about this, or you can pull this one. As I said before, I'll put these links in the syllabus, and you can just copy paste them, and you can grab the notes yourself. So we have a little bit of time before the break, so maybe we should just, how is it we get the Black-Scholes PDE derived? Well, let's just recall how to derive the Black-Scholes. So we call Black-Scholes. This model here was, sometimes it's called Black-Scholes, sometimes it's called Black-Scholes-Merton. It's actually due to Samuelson. Samuelson, he did this thing in 1969. So some people also call it Samuelson's model. So let's look at a simple case where we have the interest rate is 0. So the money market account, it doesn't change. It's just always equal to 1. Right. This is true for all t. And then you have the stock, GST, and we write down the stock dynamics directly under the risk neutral measure. So you have ds is equal to what we have here, and then you have an initial price that's positive. And so in this model, the volatility here, this is a constant sigma. So that's the Black-Scholes, and what we're interested in, you have a payoff. You have a payoff at time capital T. So let's call that for, I forget what we used to call it. I think we call it for G of ST. And so what we are interested in is the initial price. So the price at time 0, that's going to be this expectation under that risk neutral measure. So we have a martingale property under that one. You don't need to discount because the interest rate was set to 0 just for simplicity. And so here we'll have to compute this conditional expectation. And this here is our if 0 is 0. Right, that's the initial price of, that's the price at time 0 of getting the payoff G of S capital T at time capital T. And so we use martingale techniques. Right, so we look at the conditional expectation given ft, right? That's a martingale, and this is what we want to be f of t and then s of t. So the left-hand side here, this is a martingale because there's just conditional expectation. There's no little t inside here. So this is this Levy martingale that we've talked about a number of times. In your homework number 4, we've had this, we have stochastic volatility. And so if you have a sigma t here, you might need to include more terms on the right-hand side than just the stock price. You would have to include, for example, the volatility. If this was a Heston model, you would have to include S, comma, and then something with a Feller process over here, or Stein and Stein, you would have to include more processes over here. But in Black-Scholes is one-dimensional. S here is Markov. This here is this is Markov under Q. And to test for it, this is Markov under Q because the coefficient ST sigma is a function of only ST, right? So this is a coefficient in front of the dB term. If there was a drift, that coefficient would also have to be considered. But here, there's no dt term, there's just the ST sigma. And this is a function of only ST. So ST by itself is Markov. And this is what fails in your homework. When you have a stochastic process here for sigma t, then you would have ST sigma t. This is not a function of only ST. That will also require sigma t. Somebody asked about that, I think last week in the office hour session. And so because sigma is a constant here, you have that S by itself is Markov. This would never work had sigma been stochastic, then you would have to include that as well. Okay, so now given that S is Markov, then you only have to put S here together with time, of course. You only have to put S and time inside your function. And then you have to find the martingale. There's no discounting here, so you don't have to adjust it. This is a martingale, and then you just apply Ito. If you apply Ito, then you'll have the df of TST. There'll now be d terms on the right-hand side. This will be F1 TST dt. And then there will be the second derivative, F2 TST, and then the stock DST. And then because there's a Brownian motion, we also need a higher order term. There's Brownian motion inside S, so we need the second derivative, TST, and then the quadratic variation of S. And we end up here with F1 TST dt. DS, go up, we have a look at what DS is. This was S sigma. And then the Brownian motion. And then quadratic variation, 1/2 the double derivative. And then quadratic variation of S, we square the volatility, S squared sigma squared, and then the quadratic variation of Brownian motion, this is dt. Right, so this comes out from Ito. We needed to know what the Markov structure was. Then we apply Ito. Then it comes time to use the martingale property. If this is a martingale, I know that there's 0 dt plus, and then just the martingale part. This is F2 TST ST sigma dBT Q. Okay, so for that equality sign to hold, what you need is, so you need no drift. So you need 0 is equal to F1 TST. That was one term in the drift, and the other term was over here. 1/2 F22 TST ST squared sigma squared. So we're almost at the PDE, but now replace S by a dummy. So this is X. ST is positive, so we replace stochastic variable with a dummy, we're going to get 0 is equal to f1 tx plus 1/2 f22 tx x squared sigma squared. So that's one part, and then we also have a terminal condition. We also have a terminal condition, so f of capital T comma s capital T. What is that going to be? Well, if I want this to be true, I put in capital T here, then I get measurability because S capital T is F capital T measurable. I get G of S capital T. And then again, you replace ST by a dummy. And you get F of T and X is equal to G of X. And ultimately you combine to get the Black-Scholes PDE. You have a 0 is equal to F1 T and X plus 1/2 F22 T X x squared sigma squared. And then you get a terminal condition. F at T and X is equal to G of X. That's the Black-Scholes PD. Are there questions on how to derive Black-Scholes? I'm sure you guys have seen that. I have done it in class here, and for those of you that are taking 622, I'm sure you've seen it with Professor Pham as well. So often time is reversed for numerical procedures. For numerical procedures, there are two changes. One is time is reversed. Time is reversed, and the term 1/2 x squared sigma squared is dropped. So let me just show you briefly how you can reverse time. So let me talk a little bit about, if I look at u, t, and x, if I define that to be f of t minus t comma x. So I'll reverse time here, then I'll have that u at 0, this is exactly f at the end, which is my g of x. And if I look at u1, or maybe I should call, so u1, so this is the derivative with respect to t, write it out like that. This is equal to minus the derivative with respect to t of f take the derivative with respect to t, I'm going to get a minus sign. So this is minus f1 evaluated at t minus t and x, and then if I take the derivative with respect to x of u, this is the same thing as u 2 t minus t and x, and the same thing with the second derivative. Should be f here. It's f2 and then f22 of t minus. You plug all this in, you see that the only difference is going to be this minus sign here. And so what happens is that you replace the terminal condition with an initial condition, and this one here gets a minus sign, and you end up with a PDE that looks like U1 T and X is equal to 1/2 X squared sigma squared U22 T and X, and then the initial point will be G of X. So that's often used, instead of having the terminal condition here, you'll have an initial condition, and the price you're paying for that is you have to put a minus sign in front of the time derivative, and that allows you to move the time derivative to the other side. Often this term here is dropped, so this term here is dropped. So you just have, so that was add 1, so for add 2, that means that you're really looking at a U1 T comma X being just a U22 Tx, and then U0X is equal to G of X. This one here is something that I wrote out in homework 5, so let me just show you. Like, can I just drop these values? Can I just drop them without any problem? Well, let me show you the homework, and then let me talk about it for a few minutes. If I pull up that homework again that we had from before, homework 5. Where did homework 5 go? Here. So you see this here, this one here, this is the first problem. This is the Black-Scholes PDE that we had. That was the one I just derived. All right, so here you have a terminal condition, and you have the 1/2 sigma squared X squared term. And I showed you that we can just reverse time. This first part here is what allows us to replace the terminal condition with an initial condition. But you can see I'm also doing something now here to the X variable. I'm putting this stuff in here instead. So here's a new function, but now with the Y variable, which is given as this if that solves the Black-Scholes PDE, but it's now transformed in this strange way. And so you could ask, what is the PDE that G solves? And when you do that, what happens is that this term here, it disappears and becomes 1. So let me, over in the solution, it's you just compute all the derivatives, and then you just plug it in, and you get that GT is exactly GYY. So the time derivative is equal to the double derivative with respect to Y. So when I did this last year, or 2 years ago, whenever I taught the class last time, I thought that this was a good idea, because then to solve this, so the first question here does not require you to do any numerical analysis. There's no computer program needed for problem number 1. And so I just wanted the students to know that you could drop this term here without loss of generality. But I had not taken into account that the second part here is now about solving this problem here numerically. And this year I added a warning. So I do not recommend using this reduction technique here for your second problem. Like, so for problem number 2, I recommend working on this PDE. I don't recommend using this substitution here and start working on the PDE that comes out for G. This first problem is just here to show you that you can drop, if you want to, you can drop this term here. But numerically, this PDE up here is much better to work on than the one that goes through transforming it with this function we have here. Right, so that's what I mean when I say I recommend using the X variables, like those are the ones up in the original PDE number 1. I do not recommend working with these Y variables that you get out after you transform with G here. Right, so here it's written, use X variables. it doesn't say anything about you using y variables. So if you want to use y variables, you're on your own. I don't recommend it. And I know students last year, they were banging their heads against the wall because using these y variables, it really did lead to that there are issues that come out from using these y variables numerically that are not there if you use the x variables. Okay, so when you do this problem, please stick to the original Black-Scholes PDE. But I want you to know that it is possible to get rid of this 1/2 sigma squared x squared term by doing a transformation of this sort. And it's not a surprise, right? Because what the way that transformation it didn't come out of nowhere, right? For this one here, when I'm looking at the stock that I have, I have this ds here. This SDE, I know how to solve that SDE. This SDE has a solution. I have a solution. ST is equal to S0 e to the sigma BTQ minus 1/2 t. Right. So what we have here is that this one here, this ST, this is like my x variable. And then this B up here, this is my y variable in homework 5. So there's this relationship between x and y. After the break, we're going to be talking about numerical methods for this equation here. So we'll use for now. We consider this, and I'll start writing ut instead of u1 being uxx, and then I'll have u at 0 being g of x. But that being said, in the homework, you need to include 1/2 sigma squared x squared. I'm just not going to do that today. I'm going to consider the simpler version here in the lectures. And then you have to make corrections to that simpler. It's not a big correction. You just have to include these terms here in your analysis when you do the numerics. Are there any questions or comments? Otherwise, I propose that we take a little break and get back together a little bit after 10. Any questions or comments from anybody? Okay, then let's take a break, 10 minutes or so, and then get back together.